Well, good afternoon, and welcome back to NASA headquarters for part 2 of the Pluto New Horizons Encounter Briefing. I'm Dwayne Brown with the Office of Communications. In our first briefing, you heard about the incredible science and data, the timeline of history-making spacecraft, and it prepares to encounter the Pluto system in July. Now you will hear in more detail about the unique spacecraft and some challenges that they will be closely monitoring. We'll have brief presentations from our panel, then we'll open it up for questions, starting here, our phone lines, and of course social media. Social media is abuzz with this upcoming encounter and flyby. Send those questions in at #AskNASA. And as always, you can get updates on this mission, the data, images, and a whole host of other outreach and communications activities that will be accompanying this worldwide interest at www.nasa.gov/New Horizons. Before we get started, let me introduce you to the panel for our second part briefing. First up, Jim Green, Director of Planetary Science, NASA headquarters. Glenn Fountain, New Horizons Project Manager, Johns Hopkins University Applied Physics Laboratory in Lowell, Maryland. Alan Stern, New Horizons Principal Investigator, Southwest Research Institute, Boulder, Colorado. And Hal Weaver, New Horizons Project Scientist from Johns Hopkins University Applied Physics Laboratory in Lowell, Maryland. And with that, Jim, it's yours.
Thank you very much, Dwayne. New Horizons was launched in 2006. And so it's been more than 9.5 years in space. But I want to congratulate the team for getting it here. You know, for many more years prior to that, all the hard work that they've went into to be able to design, build, and get it onto the launch pad, and then get it launched. And what a marvelous machine it is. Here's a 1/8 scale model of New Horizons. Now this is about the size of a baby grand piano, but it is carrying a beautiful symphony of instruments with it that will play together all during this encounter. This is truly a remarkable machine. But this is no simple flyby. You know, Pluto is more than 4.5 light hours away from the Earth. With round trip time of 9 hours, the spacecraft has got to work flawlessly in a very automated fashion. It's perhaps one of our most automated planetary spacecraft ever launched. I also want to take special note that we're flying into the unknown. And it's really because of that that we have to anticipate not only what we think we'll observe, but also what we cannot see right now, but will be illuminated to us as we get closer and closer to the Pluto system. Now that means exciting new things will come about that we'll want to take advantage of, but we also have to be very careful that those exciting new things don't present hazards and cause some mission problems along the way. So our plan for today is really very simple. I want to have everyone take a glimpse of not only the spacecraft's fantastic capabilities and how it's going to execute this mission, but also introduce some of the major challenges that we may have to face to be able to make this mission successful. And to start off, let's have Glenn Fountain, the New Horizons Project Manager from Johns Hopkins. Glenn.
Thank you, Jim. Well, it's my pleasure today to spend a little time with you and tell you some more details about the spacecraft. You heard a little bit about it from Jim earlier today. You heard about the wonderful instrument package that we're carrying. And it's the spacecraft's job to get those instruments to the right place in the Pluto system at the right time, to point them toward the system and to be able to observe the parts of the system that we are going to investigate, and then to get the data back. So we had a number of challenges as we went in and to design this and fabricate the spacecraft. First is, it's a long way to Pluto, as you've heard, 3 billion miles. And to get there in a reasonable time, reasonable for us was 9.5 years, you had to make the spacecraft light, and you had to make the spacecraft be on a rocket and be able to withstand the environment of that rocket that went very fast to get us there. So we built a spacecraft that was about 1,000 pounds, the size, as you heard, of a grand piano. And here is a graphic that you see of that with a person standing by it, almost as though he's playing that grand piano. And it also has this big salad bowl looking thing on the top of it, our high gain antenna, which I'll speak to more about later. In my next graphic, I want to talk about the next challenge. We're operating so far from the sun that the intensity of the light is 1/1000th of its intensity here at Earth. Solar rays do not work there. Lucky for us, the Department of Energy early in the space age developed a power system that would operate in these conditions. It's called a radioisotope thermoelectric generator, R and RTG, that you see here pointed to. It uses 24 pounds of plutonium, which in its decay generates heat, and that heat is turned into electricity. We use 200 watts is what it produces at Pluto, and it's that 200 watts we used to operate the spacecraft. And the next image is how to keep the instruments and the operating, the electronics and all the components of the spacecraft reasonably warm. So we have designed a very efficient thermal blanket. That's our own thermos bottle, if you will, so that the inside of the spacecraft is operating at room temperature. It is hardly deviated from about 22 degrees for 9 years as we've flown across the solar system, while external temperatures, first near the sun, you were getting a lot of sunlight, but at Pluto as we go by, Pluto is minus 400 degrees Fahrenheit, yet the spacecraft remains quite warm. So in the next image, we go back to the salad bowl, the high gain antenna, which is the principal means of communicating between the spacecraft and Earth. Communication system uses 12-watt transmitters. Think of it as the power of 2 nightlights, 3 nightlights, I'll get it right in a minute. That is the power that we are using to signal back, transmit the data from the spacecraft to Earth over those 3 billion miles. 12 watts. And with that, we get data rates back at 2 kilobits per second in our fastest rates. And to do that, we have to point the antenna at the Earth to within 0.7 of a degree. For much of its journey across the solar system, we have operated the spacecraft in a spinning mode. We spun it up like a top with the antenna pointed toward the Earth or where the Earth will be in a few months. We would then operate the spacecraft in what we call the hibernation mode for most of this period of time. We turn most of the systems off and we let it just fly through the space, and that keeps the wear and tear down, if you will, on the spacecraft. And every month we would listen to the spacecraft, get telemetry back from the spacecraft, and we've been operating that way for these 9 years. The mid-gain, the MGA that there is, the mid-gain antenna, that allows us to have a little wider field of view for the antenna so that as we point several degrees to where the Earth will be later, we can still communicate at low bit rates to the spacecraft so we can continually keep in communication with the spacecraft. As you heard earlier, it's 4.5 hours one-way light time. So all of our observing programs have to be pre-programmed onto the spacecraft. And they're stored in an onboard computer, and then they operate the spacecraft as we fly through the system. The main part of the observing program is in a 9-day period, 7 days prior to and 2 days after closest approach. We call that the core load. That's where we get the primary science. And then we will later store that data as we go through the system on our 64 gigabit solid state recorders, and then play it back slowly over 16 months once we get the data on. So we gather the data very, very quickly because we're going through the system, and the majority of the data is only a few hours around closest approach. So that data is stored on the recorders, and then we spool it back over the next 16 months. In the next chart, I'll talk a little bit about how we point. So this is a model of the spacecraft, and as we've been flying with the antenna mostly pointed to the Earth, and then we can rotate the spacecraft, cause it to despin, and then operate it in a 3-axis mode so we can point the instruments. Here's LORRI, the long-range reconnaissance imager that you're going to hear a lot about, at various objects. We can then point using these thrusters that you see here in this image, so they allow us to slowly move the spacecraft back and forth. On the next chart, you'll see also 2 star trackers. They're right here, and they allow us to determine where the spacecraft is pointing. We also use an inertial measurement unit, which is inside the spacecraft. It consists of a ring laser gyro, which measures rates very precisely, and it has an accelerometer, so we can measure when we want to make a trajectory correction, the acceleration we're putting on the spacecraft. With these components and a guidance and control computer, we can point the spacecraft to better than 1/10 of a degree, and we can control the rates of motion to 1/1000th of a degree per second. So we get very precise pointing, and that's how we take the data as we go through the system. So next chart, I want to talk a little bit about the resiliency of the spacecraft. We're going a long way. This takes us a long time to get there. So we built a lot of redundancy in the spacecraft just in case some component fails. So far, nothing has failed. But we're prepared just in case something does fail. For instance, in this diagram, you see that we have 2 integrated electronics modules. Those contains our guidance control computer, our command and data handling computer, our solid state recorder, and some other electronics. On the next chart, you'll see the transmitters. We have 2 transmitters and 2 receivers. And the next chart, you see that we've got 2 IMUs, inertial measurement units. And in the next chart, the 2 star trackers I talked about. And in the next chart, you see a number of thrusters. We have sufficient thrusters on the spacecraft so any one thruster could fail and we can still complete the mission successfully. So all of those systems we've carried along and still maintain the mass we needed, the weight we needed to get there in 9.5 years. On the next chart, I want to talk about the other part of how you make use of this redundancy. It's called the autonomy system for fault protection. So we have a computer program that runs on one of our computers, and it checks the system to see if any component is having a problem. If a component is starting to fail, it will switch the system to the other redundant component. And it will then send a signal back to Earth and say, hey, something's gone wrong. You ought to intervene and see what you need to do to be sure I'm doing everything right as far as the spacecraft is concerned. However, when we're in that 9 days around closest approach, we want to take data, stay to the observation plan that's already been pre-programmed that you heard about earlier, to be sure we get the data, because in that period of time, getting the data is more important than having the spacecraft operators intervene. We believe that the spacecraft can perfectly well take care of itself during that period of time. So that's how we carry the fault protection and have enough onboard autonomy to assure that when we get there, we get the goods. So I'd like to then talk a little bit about the way we get there. So We use a navigation process that's been used classically. And over these 9.5 years, we've had to make 7 small corrections to our trajectory. The last one was last March. And so to give you some perspective, we're traveling over 30,000 miles an hour. And we made a change in the velocity of the spacecraft of about 3 miles per hour. That's the kind of correction we've had to make to be sure we get to the target that we're going after, to get into the Pluto system, and we had to fly through the system at exactly the right point. Up until this point, we have been using what is the classical Doppler navigation techniques. We've been looking at the changes in the frequency transmitted from the spacecraft to determine its velocity, and that is how we've been navigating the spacecraft until this last summer, when we began using another technique called optical navigation. Optical navigation allows us to use the onboard instruments, particularly LORRI, to observe the system and then compute on the ground with our navigators where the spacecraft is precisely with respect to Pluto. And I'd like to run an animation that'll give you a little sense of that. So in this animation, you see the spacecraft moving along the trajectory. The green line is where we've been, the red line is where we're going. And we then take images like you see here with LORRI. So this is an image of Pluto, and we observe the star pattern behind Pluto. And as we move along the trajectory, you'll see the stars move relative to Pluto, the apparent motion, just like when you drive down the road and you watch the telephone poles move relative to the background. And then we get a little bit further along, we take another image, and we can use those images to work out the geometry and compute exactly where the spacecraft is and where we need to send it. Now, we need to send it to a very precise point. As we fly by Pluto, we need to hit a target that's 60 by 90 miles, and we need to hit that target, as keyhole, if you will, within 100 seconds. So we're flying 3 billion miles, we have to hit a target 60 by 90 miles, and we have to hit it within 100 seconds after 9.5 years. That's the kind of precision we have to navigate to. Then we fly through the system, and with this next graphic, you'll see the path through the system. Here you see the Pluto system, which is inclined at about 46 degrees with respect to the path we take through the system. So not only do we have to hit this one point in the system as we fly by at closest approach, but we have to also fly through in such a way we have to thread the needle so that we pass through the shadow of Pluto and then the shadow of Charon, just to make it just a little more difficult. And that's what our navigators and our mission design team have to do. And with that, we collect the data, and then we turn around and we get it home. And with that, I'll turn it over to Alan, and he can tell you about some of the things we're going to worry about on approach that I haven't talked about yet.
Glenn just did a great job of telling you about some of the design challenges that we had in building a spacecraft to fly so far from the Earth, to operate so far from home as well as so far from the sun, to take care of itself autonomously, etc. And that was a great one-on-one on the engineering challenges. What I want to tell you about are some of the environmental challenges. That is, playing off Jim Green's terminology, we are, as a mission of exploration, flying into the unknown. And the Pluto system itself can present hazards to the spacecraft. Now, this is not entirely new. In the first missions to cross the asteroid belt or to explore Saturn's rings in the Saturn system, the first missions to go into Jupiter's intense radiation fields, there were hazards of various types that spacecraft teams had to deal with. In our case, with New Horizons, our primary concern is about the possibility of collisions with small debris in the Pluto system. Now, when the spacecraft was first designed, it was designed with a Kevlar jacket to protect it from micrometeorite impacts. And that's a very good shield for crossing the solar system. But with Pluto, we have a little bit different challenge, and I want to tell you some of the background about that. But let me first stress a difference between New Horizons and some of the early exploration missions that had their own challenges, as I just said. In the case of New Horizons, we have precisely one spacecraft and one chance at returning the science from the Pluto system. There's no Voyager 2 equivalent. There's no Pioneer 10 and 11 pair here. It's just one spacecraft that has to get it right and that needs to make it through the system so that it can transmit its data back to the Earth. So let me begin with a little bit of the astronomy of the Pluto system and very quickly illustrate what the concerns are and the challenges are that we're dealing with. On your screen is a view of one of the Discovery images from 2005 made by the Hubble Space Telescope of the first of two of Pluto's 4 small moons that have been discovered, Nix and Hydra. And at the time that we used Hubble to make those discoveries, we actually scoured the data that was available to see if there were additional moons in the system. And we didn't find any. We found Nix and Hydra, but no more. And that persisted for about 6 years. Then, if I can have the next slide, in 2011, Hubble was used again with even more observing time that allowed us to penetrate deeper. And lo and behold, we found another moon. And then next view graph, in 2012, we looked with Hubble again, and we found yet another. So a total of 5 moons, 4 small moons, and it seemed to our team that every time we look harder, we find more satellites. Now, our concern is not that we might hit a satellite. We can do those calculations, and even if there were a very large number of satellites in the system, the odds of hitting any one are very, very low. The problem is this. The Pluto system is flying through the Kuiper belt at about the speed of a bullet. That's Pluto's orbital speed. And the Kuiper belt itself is filled with debris, which strikes Pluto. No problem, because when it does, it makes a crater, and Pluto's gravity just causes all the spray that comes out to fall somewhere on Pluto's surface. That same Kuiper belt cratering process strikes Charon, the big Texas-sized satellite, and it has enough gravity that the ejecta also just flies suborbitally around Charon and lands somewhere else, like on our moon or like on other icy satellites. But the small moons, because they're low mass, have very low escape speeds. And when they're cratered, the ejecta, the spray that comes out of the crater, gets into orbit around Pluto. And tiny particles, even the size of rice pellets, can be lethal to the New Horizons spacecraft because we're traveling so fast, 30,000 plus miles an hour. So we developed a concern that the Pluto system may have unseen debris, either due to satellites we haven't discovered, due to rings that are consisting of small particles, or due to ejecta that comes out of the craters on the satellites that we do see. And this was back in the 2011 timeframe, about 4 years ago. And so we put together a hazard analysis team within the New Horizons project. And they began to analyze this problem. They also went back and took spare parts left over from the construction phase of the spacecraft and retested them to determine their hardness against impacts. If I can have the next chart, the basic problem is a double-edged sword. When you find small satellites, as a scientist, you're very happy that there are more things to study in the system. But because those small satellites can generate hazards of their own, there's also a concern generated by the same thing that can be a scientific bonanza. If you look at the next time step, you'll be able to see a graph with time along the horizontal axis going from 2011 to the present day. And then on a logarithmic scale, factors of 10 are estimates from modeling and testing of what the probability of a loss of mission or a severe impact onto the spacecraft might be. And you can see back in 2011, the earliest, simplest calculations led us to believe that this could be a real concern. But as we added more and more fidelity, more physics to the models, and as we did more testing of the spacecraft components back on Earth to determine their hardness, our degree of concern declined with time. And you can see that directly in the plot. In fact, the very best model estimates that we have today indicate that the probability of something severe happening to New Horizons is very low, significantly less than 1%. In fact, around 1 in 10,000 is our best estimate. But nonetheless, even though we predict that the chance of something untoward happening is very low, we want to make sure that we've taken every precaution to have a successful mission with New Horizons, particularly if we discover things that we don't expect or that the models, such as in this graph, don't predict. So I'll step to the next time chart and tell you about what we've done. And I want to summarize several things. First, we put in place plans, which will begin in May, next month, to image the Pluto system with the LORRI imager very intensively, to make very deep images from on the scene, on approach to Pluto, to look for new satellites or possible rings that could present hazards. I'll say more about that in a minute. We also put in place plans to be able to divert from our nominal path through the Pluto system, the green path shown in this graphic, to one of the neighboring yellow pathways that give us alternatives through the system so that we can move over and redirect the spacecraft if we find something in those hazard images. Now, those don't come for free. The alternative trajectories called Shabbats, the yellow ones, which are called Shabbats, have less science potential. Now, it may be necessary if we find something that's concerning about the survivability of the spacecraft to lower our grades a little bit to make sure that we don't fail at the Pluto system due to those hazards. And we're perfectly prepared to do that. And we've practiced that in simulations, and we have the burn targets already computed so that we're ready to go if we need to select one of those alternate encounters. The other thing that we've done is that we put in place some science downlinks just 2 days and 1 day before approach to get some of the very best data off the solid state recorders and down to the Earth as a just in case, like Neil Armstrong's contingency sample that he picked up before he did much of anything else, to make sure that he had something in his pocket in case he had to return up the ladder. By analogy, we want to make sure that we have some of the very best data on the ground before we pass into the heart of the satellite system and take any possible risks. So we've done all of that. We've made all of those plans, and now we're on the heels of the beginning of that watch campaign. So if I can have the next time step, you see listed on the left in that little table the dates of the first days of each of a series of campaigns, 2 in May and then several more in June, as we get closer and closer into the Pluto system. And on the right, you see those squares that are overlapping fields of view from the LORRI imager compared to the orbits of Pluto's known satellites. And we'll be very intensively obtaining those images and sending them back to the ground and analyzing them on the ground to determine what we're finding. If I can have the next time step, you see what the system will look like as we get much closer, late in the month of June, just weeks before final approach, when we're very sensitive compared to any telescope back on the Earth, and can really search for much smaller satellites that have been discovered, search for debris sheets or rings that could give us pause. So I think you can see that we're taking this very seriously, but I want to emphasize, and I'll do this with the last time step, that our very best knowledge of the Pluto system is that it does not present any hazard to the spacecraft. Nonetheless, we have planned a very extensive 7-week campaign to study the system as we fly up to it and to be prepared to take alternative courses through the system. If needed, our backup plans are fully in place, fully practiced, and we'll be reporting on those results to you every time that we collect hazards data so that you, like us, know what we're finding and if we have any concerns. If you remember from NASA's spectacular Curiosity lander, the phrase 7 minutes of terror on landing, I like to refer to the approach to Pluto as 7 weeks of suspense. So stay tuned, and we'll let you know the news as it develops from the frontier on the far side of the solar system. And now, having told you about the challenges to the spacecraft, as Glenn did, and the challenges of the Pluto system, as I just did. Hal's going to talk about the opportunities. Hal?
Okay, thank you, Alan. Hello, everybody. So if I can have the first graphic, please. So what we're going to do with the New Horizons mission is turn this pixelated blob into a real world with complexity and diversity. Now, that when you think about this image, though, this is the best you can do from the Earth. It's actually pretty darn good. Pluto is about 1,500 miles across, but you're observing it from 30 times farther from the Earth than the Earth is from the Sun. Okay? And what we've learned from 50 years of space exploration is that if you really want to learn details about planetary objects, you have to go there. And that's what the New Horizons mission is going to do. Just 3 months from today, we'll pass within 8,000 miles of the surface of Pluto. And that's going to enable us to see Pluto in high definition and in color. If I can go to the next graphic. So just 13 minutes before the time of closest approach is going to be our highest resolution imaging. These will be black and white images that we take of Pluto as we take, this is a still from a scan that we'll make across Pluto. The little orange square near the center of that object there, this is a representation of Pluto with our best current knowledge of what the brightness variation is over the surface. That's football field size resolution. 75 yards is the size of the field of view there. At the same time, we have our color imager with all of those other rectangular lines, the long, narrow things. That's the IMVIC color imager. As we're sweeping across Pluto, we'll take data with both that instrument and with the LORRI high-resolution black and white imager. If you go to now I actually want to show you an example of that scan that we'll make with this movie. If you could start that, please. Near the center, it gives you the global view with Pluto at the center, and you'll see Charon right next to it. And Charon now goes behind Pluto. If you look into the upper right, you'll see a magnified view of what is being centered in the field of view of the cameras, and you'll see Pluto passing through. We get a swath, football field size resolution of Pluto as the spacecraft scans across it. This is going to be phenomenal. Of course, we don't know what we're going to see. This is one of the main objectives of the mission. What does Pluto's surface really look like? What does Charon's surface really look like? Are there mountains? Are there valleys? Are there geysers? This is why we're going there. One of the main reasons, one of the 3 reasons. Okay, if you can go to the next graphic. One of the other most important objectives of the mission is to actually map the composition of the surface over the entire surfaces of both Pluto and Charon. If you can go to the next graphic, please. And we do that with a near-infrared spectral imager called LISA. The best we can do right now from Earth is a global view. And it's already been very interesting. We can tell there are very exotic ices on the surfaces. If you look to the left there, that's the spectrum of Pluto. All of those dips, what those are fingerprints of exotic ices on the surface, molecular nitrogen, methane ice, and also carbon monoxide ice. On the surface of Charon, you have plain old water ice dominating the surface. But what we're going to do with the New Horizons spacecraft and the instruments on the New Horizons spacecraft is actually more than 65,000 footprints on Pluto and Charon, where you can now map the distribution of these ices, and it'll be more than just what you see here. We'll discover new molecules, new species, organics on the surface, be able to map those over the entire surfaces of both of those objects. Okay, if we go to the next graphic, the other big objective of okay, so I don't want to forget about Charon. If you can go ahead and start the movie here, we're going to do a similar scan. This will be about 14 minutes before the time of closest approach to Charon. Well, we'll get resolution black and white in our black and white camera of about 175 yards across. Not quite as good as Pluto because it's a little bit farther away, but as you go ahead and sweep through, you saw the fields of view of both the LORRI high-resolution imager and the IMVIC color camera sweeping across Charon. And so we'll be able to map the surfaces of both of those objects. And the other cool thing that we're going to do with Charon, actually, is after we fly by Pluto and look back, it turns out because of the geometry, Charon is closer to the spacecraft than Pluto is, and so we actually use sunlight reflected off of Charon to illuminate what would otherwise be the dark side of Pluto, and we can measure that side of that hemisphere of Pluto at much higher resolution than we could on the incoming observations. Okay, so now those are the two objectives that we just now talked about. Now we're going to go to the third major objective of the mission, which is the study of Pluto's atmosphere, which coincidentally is primarily molecular nitrogen, just like what we have on the Earth. But there's a really cool set of experiments that we do that are highlighted in the middle of the frame there. After we pass by Pluto, we then fly into Pluto's shadow at the same time while we're looking at radio beams coming up from the Deep Space Network, being beamed up to the Pluto to that radio dish, and measuring the structure of Pluto's atmosphere, the temperature, and the mass of Pluto's atmosphere. At the same time, the ultraviolet spectrograph, the ALICE instrument, will be observing the sun, and by looking at the absorption of sunlight as we pass behind Pluto's atmosphere, we'll get the signature of all of the composition of Pluto's upper atmosphere. Hydrocarbons, molecular nitrogen, and other things. In addition, after we've flown by Pluto, we'll also put the instruments on the little crescent, have them centered on the crescent so we can map any hazes in Pluto's atmosphere. And then finally, in addition, we have these two instruments, SWAP and PEPSI, which detect charged particles. And they're going to be sensitive to the escaping atmosphere coming off of Pluto and measuring how much of Pluto's atmosphere is being lost to space. So if you go to the next slide, we have more, as you've heard. We have this amazing system of satellites in the Pluto system. 4 small satellites. We know, if you thought it was hard to observe Pluto from the Earth, so far away, 3 billion miles away, it's even harder to get any information on these small satellites. But by passing close by, as the New Horizons spacecraft we'll be able to get we'll be able to see finally what these small satellites look like. We can't tell now whether they're 30 miles across or 100 miles across. They're probably highly elongated objects, what their rotation rates are and so forth. What do they look like? Here's some examples of icy satellites in the Saturnian system along the top there, and then one of the small satellites of Jupiter down below Amalthea. Might look something like this, but who knows? We're talking about the Pluto system, much farther away from the sun. It'll be very interesting to see what those surfaces look like. And that's what we'll be able to do with the New Horizons spacecraft. Okay, if we go to the next slide, in addition to just measuring the sizes, the shapes, what the surfaces look like of the small satellites, as Alan just said, we're going to be doing some very deep imaging to look for new satellites. We might discover some other ones, and we'll be looking for these dust rings. So we go to the final slide, just point out that this is the best ever initial reconnaissance of a planet in our solar system. This is the initial exploration of this whole new zone, the Kuiper Belt, that we didn't even know existed until the early 1990s. This is our first step into this new land, and we're going to be applying sophisticated modern instrumentation, a very comprehensive science program, and squeezing out as much as we possibly can, because this is truly a once-in-a-lifetime opportunity. The one other thing I want to say is that even though we have a laundry list of specific scientific objectives that we're addressing, the thing that we also have learned from the 50 years of space exploration is when you go somewhere new, we haven't been there, done that in this case, you're going to learn something you probably could never even imagine. And that's going to be part of the excitement of this mission. So 3 months from now, remember, visit us at the New Horizons, at the Johns Hopkins Applied Physics Laboratory, where all the data will be coming down, and we'll have an opportunity to see what the Pluto system looks like. Thank you.
Unique spacecraft or unique mission? Thank you all. Okay, so in the first briefing, I started with the phone lines. I didn't get a chance to see if any of our folks here visiting headquarters have any questions. If you have any questions, please raise your hand. If not, we will go to social media. We'll take up. We have, and please wait for the mic. Identify your name and affiliation, please.
Can you hear me?
Go ahead.
Yeah. Shelley from Discovery Channel. So I know it's very exciting about these satellites that could be discovered, also very concerning. I'm just curious about the timeline between now and July. When you think you might be able to see things that could be satellites with low mass, that could be the source of more debris, hazards, that kind of thing?
Okay, I'll speak to that, and I'll tell you a little bit about the associated timeline of how we would react to that. The initial imaging that I showed in my package that's going to be made in May is going to be competitive with, but not significantly better than, the very best imaging that we can do from the Earth and Earth orbit. But as we get into June, and particularly late June, in the last couple of weeks of June, we're going to have significantly better capability in those last 3 sets of hazard imaging to finding the small satellites and rings that you're asking about. And so we'll be downlinking images at the fastest pace that the spacecraft can handle and getting them into the hands of the hazard team to look at those data, to make an assessment of what we're finding and whether anything that we're finding can generate a significant hazard. And we're prepared to use the engines on the spacecraft within a matter of days, if necessary, to divert. We also have the option to change the onboard sequence so that instead of letting the spacecraft point at every target in the system freely, to use this high-gain antenna as a shield by flying the high-gain antenna forward, what we call in the ram direction, to shield most of the body of the spacecraft from any hazards. And we can make a decision to do that as late as just days before arrival. We can make a decision to divert to one of the alternate Shabbat trajectories as late as about 10 days before encounter.
Any other questions here before we? Yes. Well, you wait for the mic and identify name and affiliation, please.
Nola Red, freelancer. Just as a follow-up, how would that affect communications, or how could that potentially affect if you're using it as a shield?
That's a very good question. So in fact, on encounter day, the day that we're going to fly through the satellite system, we actually won't be using the communication system, the spacecraft, to talk to the Earth at all. The spacecraft's going to be busy taking data. So even if, whether or not we pin the antenna into the ram direction as a shield will make no difference in what communications we get back from the spacecraft. On the day of July the 14th, the spacecraft will be busy at Pluto and not talking to the Earth until late in the evening, East Coast time, when it will check back in and tell us how it's doing, give us a health report, and then go back to data taking again within less than half an hour. The first downloads won't come until the morning of the 15th, when you'll start to see imagery from closest approach, and that will happen whether or not we've made an antenna to ram decision or not.
But let me answer another part of what your question sounded like it was getting at. Putting the antenna forward and having, if we should have a particle hit it, we'll pull a hole in the antenna, but it'll be so small that it will not affect the communication.
Good point.
Okay, what we're going to do here is we're going to, social media is a buzz as usual, and go to my colleague from the Applied Physics Lab, Michael Buckley, on social media, and then we'll go to the phone lines and come back here and wrap up. Mike, what's going on in the social media world?
This is one of those questions that kind of seems easy when you start, but then a little hard to answer. Is what are you most excited to learn about Pluto from this mission? And then how will this mission impact future ones?
Why don't we each take a turn at that?
Okay, from my perspective, this particular body is a very special one. You know, it's learning something about a whole new population. Now we have opportunities also to make comparisons. Well, we have Dawn now at Ceres. Ceres might be related to the Kuiper Belt in some way. We really don't know. We have another body that's a moon in the Neptune system called Triton. There's speculation that perhaps Triton is a captured Kuiper Belt object. So those are very tantalizing pieces of information that once I think we see Pluto, we're going to be able to make great progress in understanding how these objects are related, and therefore begin to understand how they got to where they are. You know, what was the dynamics within our solar system that moved these bodies around, got captured perhaps, or put in the asteroid belt, and how did that happen? And those are huge steps for us.
And for me, there's the comparisons that we've already had in the solar system. How is Pluto alike or different? And I'm always in love with geography. So I'm interested in the geography of Pluto. And that will be exciting. We get these images back, we look at the topography, we look at the geology. That's going to be an exciting piece of data for me.
Well, I want to answer this in three parts. I want to first say that I've been working on, as a member of the scientific community, I've been working for over 25 years now, since 1989, to see a mission fly to what we used to call the last planet, what we now know is the archetype of the third class of planets in our solar system. And so at one level, more than anything else, I just want to unwrap that Christmas present that's been under my tree for 25 plus years and see what's inside. My technical specialty is the second part of the answer, because I'm very interested in Pluto's atmosphere, its composition and its structure, and what the Alice and Rex instruments particularly have to tell us about this exotic kind of planetary atmosphere that can actually teach us about some of the conditions on the early Earth. But I want to leave you with one thought. It may be a long shot or it might not be. I want to leave you with one word: liquids. I think one of the most interesting things that we can do with New Horizons is look for cryogenic liquids on the surface or in the interior. In the interior, like an ocean, as Bill McKinnon spoke about in the earlier panel. On the surface, there are many fewer possibilities, but there are materials like neon, for example. There could be rivers of neon that have been speculated about, or evidence of past liquids flowing on Pluto's surface. And that, I think, is something really exciting that we're going to be able to test.
Yeah, so I can't really say any better, about the scientific objectives of the mission, but what I'm really looking forward to is, what does Pluto really look like? Is this it behind us? Does it look anything like this at all? I mean, it's this is our best, just knowledge of what we already know about Pluto and Sharon. And we have these astronomers have spent a lot of time trying to, use the Hubble data, the brightness variations over the surface and the color measurements to sort of figure out, how much variegation, how much coloration there is on Pluto and so forth. But really, I can't wait to see those high resolution images that we take near the time of closest approach and see what it really looks like.
Okay. Mike, before I ask for another question, this is being seen all over the world, so I want to make sure, because I kind of didn't do you justice on exactly your organization. I want to say the Johns Hopkins University Applied Physics Laboratory. Okay. What you got?
Okay, so here's another more of a technical question, but timing is crucial during the New Horizons flyby to collect data. So how challenging is it to choreograph that dance on July 14th?
I'll talk a little about it, and I think Glenn would like to as well. As we've told you, the entire flyby is scripted, and the specialists in the planning of the sequence start with what our scientific objectives are, which are translated by the science team into requests for particular observations. These kind of spectra, some other kind of images, observations of the atmosphere or the surface, as it may be. And then the sequencing specialists use computer-generated animations from the actual trajectory that we will fly in the known orbits of Pluto and its satellites to predict when the best time along the trajectory is to make each type of observation. And then they sequence those in, one at a time, starting with the highest priority and then filling in with successive levels of priority. But it's a little bit more complicated game than that, because like any real-world problem, there are uncertainties. Small uncertainties in terms of the position of Pluto and its satellites, because we don't have perfect knowledge, and uncertainties in the knowledge of exactly when the spacecraft will arrive. As Glenn said, plus and minus 100 seconds, which is amazing after a 10-year journey. But nonetheless, in 100 seconds, New Horizons moves almost 1,000 miles. And so there can be some significant parallax in looking at the satellites and the planet itself. And so we take that into account too, by taking extra data. If the scan is predicted to need X number of degrees to cover the surface of a given body, we add margin on the ends of it to take into account the potential for those unknowns. And we add those pads specifically so that we can be sure at very high probability that each observation is captured. And then that's what gets sequenced in.
So, yeah, let me borrow this again and talk a little bit about the one area that we can't do justice in testing on the ground. We have a simulator, so we can simulate all the commands being generated, be sure all that command sequence is properly defined, it turns the right instrument on at the right time. The one that's very hard to do on the ground is to simulate the motion of the spacecraft. And so one of the big concerns, and our guidance control experts take a lot of time at this, is first simulate it on software on the ground. And then, as Alan said, we did a test. We did 2 tests. So during the closest approach, when we're the busiest and we're moving the spacecraft around, pointing the instruments, then turning back eventually to point the antenna back to the Earth, pointing back so when we pass in the shadow of Pluto, we are sure to be looking back toward the Earth and the Sun. All of that has to be timed precisely. We have to have the motions done precisely so that when we get to the point we're going to make the observation, the spacecraft is still. And we did that by doing 2 tests on the spacecraft, one in 2012, where we did that very busy time right around closest approach. And then in 2013, we did the entire 9 days. And for me, the most important thing about that test was to see that the spacecraft motion did exactly what we expected it to do, which it did.
Okay, let's go to the phone lines, and then we'll come back here and we'll wrap up. And I believe first up is Alan Boyle from NBC. Alan?
Thank you. I wanted to ask about the global coverage of the imagery. Since you're going through the shadow, how wide will the coverage be? Will you be able to create a high-resolution global map of Pluto as well as Charon, or will there be some things missing just because of the trajectory?
I'll take a crack at that. Alan, it's a great question, and people ask that question to those of us on the science team when we give public talks. So this is a good one to answer in this forum. Let me start by saying that much of the imaging that we'll be doing, the global imaging, will be with the LORRI instrument that we've spoken so much about. It's a telescope that feeds a CCD camera, and its telescopic capabilities are very important because Pluto itself rotates on its axis very slowly. It takes, in fact, 6.4 days, almost a week, to turn on its axis. And one consequence of that is that we will fly by one hemisphere of Pluto, and by the way, Charon has the same rotation period, one hemisphere of Charon, and be able to image it with LORRI and with our Ralph color and black and white cameras as well, with the kind of resolution that Hal was talking to you about. But the other hemisphere, we will last see half a rotation or 3 days before, when the spacecraft is still millions of miles from Pluto. LORRI, because of its long focal length, its magnification capabilities, allows us to do imaging of the far side hemispheres 3 days out. It's actually very good. It's the reason we put LORRI on the spacecraft, because it gave us a competitive edge in doing more science, even from afar. And the kind of imagery that you'll see of the far sides of Pluto and Charon are comparable to what you might see if you took a pair of garden variety binoculars out and looked at the Earth's moon. So pretty good. Now, there are still some other terrains, and I'm giving you a very detailed answer, but there's still some other terrains that are difficult because Pluto, being tipped on its side, as Glenn showed you, has the equivalent of the Antarctic polar night, where in one hemisphere, there's never any sunlight in 2015. And so what we've done for that is we've arranged the timing of the flyby, the day of the flyby, to be such that Pluto's giant moon Charon is behind Pluto and casting its own moonlight back into those permanently shadowed regions. And after we pass the planet, we will look back again with the LORRI camera. It's a tough experiment because we have to look back into the glare of the sun, and we will use Charon moonlight and attempt to map those final terrains, the polar terrains, in this very difficult experiment looking back into the glint of the sun. And we'll have to see how that actually turns out, because it's very challenging for the LORRI instrument. But whether or not that last piece falls into place, we expect to have nearly global maps of Pluto and Charon, and pretty good imagery of the other 4 small satellites as well.
Any last question here before we wrap up? All right, I want to thank panel here and our previous panel, ladies and gentlemen. Today, you've heard about the Pluto New Horizons mission, historic. You heard the science, the expected images and data, the spacecraft, and the challenges. I believe, Dr. Stern, 7 weeks of suspense. Did I get that right?
Got it.
Social media is abuzz with that, as I'm being told. So for the media watching this and listening and on social media, there will be a number of worldwide events, public outreach, education, and of course, media activities. Stay tuned for updates on that, working with my colleagues. We will get you a timeline of those events, logistics, etc. Sometime in the May or June timeline. There will be a host of events, and I know the media particularly will want to know the logistics on getting on the site. July 4th has its own fireworks, ladies and gentlemen. NASA will have equally exciting, if not more, fireworks for July for the historic encounter of Pluto. You can go to www.nasa.gov/New Horizons for updates. Save the date. Pluto, here we come. Thanks for joining us.